In this video, let me introduce a new term that is called shadow price. Shadow price is really related to what we've seen in the last video. In the last video, we changed the right-hand side of a constraint and see what value of the change in the right-hand side will keep our current solution optimal. So in practice for decision maker, it is important to know how the change in the right-hand side affects the optimal z-value, because the right-hand side usually shows the availability of resources. So you would like to know if the number of resources change, how it would affect your profit, for example, right? So here we are going to see how the change in the right-hand side affects the optimal z-value, such that we now may define the shadow price for the ith constraint of a linear programming is the amount by which the optimal z-value is improved if the right-hand side of the ith constraint is increased by 1. So several things I would like to emphasize here. The first thing is that the shadow price is always for a specific constraint. So shadow price for the ith constraint. Let's say for finishing constraint, for carpentry constraint, for demand constraint. So you cannot just say it's the shadow price. You must say the shadow price for which constraint. Okay, so that's the first thing I like to emphasize. Another thing I like to emphasize here is that the shadow price is always defined by this: if the right hand side is increased by 1 unit. So always 1 unit. Okay, so that's the definition of the shadow price for a particular constraint. And then we may use this shadow price for a particular constraint only if the change in the right hand side of the constraint I leaves the current basis optimal. Okay, so to make this sentence more concrete, let's say the shadow price for the finishing constraint is, let's say, $10. Then you may apply this shadow price saying that, okay, I increase finishing by 1 hour and my profit will increase $10. And then you may say, if you increase the finishing hour availability by 2 hours, then your profit will increase by $20. Well, you may do that if you already check that increasing 2 hours of availability of finishing hours keep the current basis optimal. Okay, so you may only use this definition of the shadow price of the particular constraint with respect to change in the right hand side only if that change leaves the current basis remains optimal. Let's see a more concrete example from the Dakota problem. So we know the change for B1 finishing constraint, as long as it's in this range, or this is the range of the change, then the current basis remains optimal. And then here's the value of x1, x2 with respect to the change of the first constraint. If we calculate the z, we see that z equals 180 plus delta. In other words, whenever you increase the finishing constraint by 1, your z will also be increased by 1 times delta, 1 times the change. In other words, the shadow price for the finishing constraint is $1, because when you increase the finishing constraint by delta, then the z will also increase with plus 1 times delta. For the change in B2 carpentry constraint, we may do the same thing. So we compute how that change affects the values of x1, x2, and then we compute the z in terms of delta. Again, same here, because delta is the change of the carpentry constraint. You see that for 1 unit of change in the carpentry constraint, your z will also be increased by 1 time delta. So the shadow price of carpentry constraint is also $1. Now for the third constraint, the demand constraint, if you compute the value of x1, x2, they are not affected by the change in the demand. Okay, so here you can see that when you calculate the z value, it is still just 180 without any delta term involved here. So in other words, the shadow price of the demand constraint is 0. So when we increase the demand from 40 to 41, it does not affect the z value of the profit that we get. Remember that this result only applies whenever we are staying in the boundary where the change will keep the current optimal solution or optimal basis remains optimal. Once we have obtained the shadow price, we may use it to calculate the new optimal z value. So for maximization, the new optimal z value is the old one plus the shadow price of the ith constraint times how much change you make to that constraint. Remember, the change must be in the boundaries such that the current basis remains optimal. Similarly, for minimization, the new optimal z value may be obtained from the old z value minus the constraint i's shadow price times the change that we make to the ith constraint. Again, remember that this change must be in the boundaries such that the current basis that is optimal remains optimal.